Hello, can you hear me? Hello, can you hear me?
Hi, yes, we can hear you.
Okay. Let me upload the. Okay. So I am uploading the PDF of Lab 1. You can access it from the Canvas. Um, I have not uploaded it yet. I'm just uploading it right now. So it is ELC 333 Lab 01. Can you access that?
Yes,
Okay. So this is the lab document for the first lab. And I will also go through that with you. Just a minute. So those who have sent me their group names, I actually made breakout rooms for them. And those who have not sent me, we will see that what we can do, okay? Okay, let's start. So you can see this PowerPoint.
yes,
Okay, so this lab, the document is about basic operational amplifier circuit. And so the circuit, what it is doing and what it is about, we'll see that. So objectives of this lab is that you have to um, be familiar with the software. It could be Cadence and it could be LT Spice, whatever you like to work on. Then we have to use basic electronic laboratory equipment, design, construct, and test a basic operational amplifier circuit. So all of you got the equipment kit,
Yeah.
and if any of you who doesn't didn't get it can message me in the chat, or I actually told that you can email Mike Steele to schedule the pickup. Okay. Um, So in this today's lab, we are not doing um, experiment using the kit. We are doing what you should say simulations and what you should say the calculations for the first lab. Okay, so let's see. So in this lab, what we are doing, this experiment is about that we are comparing um, actually it's a comparator we are making. We are saying if V in voltage 1 voltage is greater than V in 2, then it will be, your output voltage will be high. And if it is less than the second voltage, your output voltage will be low. So we are comparing two voltages and currents. For that, we are using operation amplifier as a differential input, and who has a differential input and very high gain. And this parallels the characteristics of a comparator and can be substituted in application with low performance requirements. Okay. So what we are doing here, so this is the task we are doing. We are saying that we are designing an alarm that will trigger if your load resistance is exceeding the current 10% above the 50 milliampere. So that's what we are doing. So in this case, Opamp takes what you should say, a certain voltage supply. So in this case, the supply we are giving is 12 volt DC and minus 12 volt DC. So it will produce 12 volt plus 12 volt DC, or our red LED will light up if current exceeds 1.1 of IL nominal, which is 50 milliampere, and it will light green if the current is less than 1.10 IL. So 1.10 IL means that you have to multiply 1.1 multiply by 50 milliampere. Why we are multiplying 1.1? Because it's like, um, what is this? Is it, why it's not writing? 1 minute. Ah, okay. Just a minute. I don't know. Okay, so 1.1 means that 100 plus 10%, like 100 plus 10, right? So it will become 10% more than 50 milliampere, which is 55 milliamperes. So you are multiplying 1.1 into 50 milliamperes, right? So that's what we are doing. Okay, so this is the circuit we are making today. Okay, so in this circuit, if you see, so what is happening in this circuit? So this is, the red box is our alarm circuit. Okay, so in this circuit, if you see, this is our source. Okay, what we are doing, we are giving a 12 volt source, and this is our load resistance, and this is our RM, which is very, very less than RL. So what we want, that all the current that is producing will go from here to here. Now, this is your amplifier, which is in the non-inverting configuration. So all of you know about amplifier or not? Jack, Delvish, wait, I don't know. Jack, do you know about amplifier? Opamp?
Okay. Yeah. Could you repeat the question? I'm a little lost. I got a little sidetracked.
I said that, do you know about Opamp? Have you worked on Opamp in last semester? Like the, I don't know.
Yeah, we worked with amplifiers in ENG 214 and a little bit with 212 when we learned a little bit about them.
So you did work on 214, like ENG 214?
Yes.
Okay. And Sean Burtnett, do you know about op amps?
Same as Jack. Yeah, I learned it in ENG.
Okay. So yeah, that's what we are doing here. what we are doing, we are using it in a non-inverting configuration. If you have worked on op-amp before, you know that the gain of non-inverting op-amp is 1 plus R2 by R1. We will explain it later. But here what we are doing is that we are using it in a non-inverting configuration. So what is happening when the current is going from here to here, and it's in the non-inverting configuration, the output it produces is the input voltage multiplied by the gain factor. And input voltage in this case is ILRM. So here you are having a output which is equals to this. Now you are comparing, so this is the op-amp you are using in open loop gain. I will discuss it what it is. So what is this doing? It is comparing these two voltages. So whichever is bigger will turn this into plus 15 DC voltage DC or minus 15 voltage DC. Means that if your current is load current is greater than IT, which is this reference current we are measuring, then your red LED will light up, otherwise your green LED will light up. So basically this op-amp is comparing the currents. Here we are, this voltage we are setting as a reference to compare the current. So essentially what we are doing is that we are comparing two currents that if one is greater than other, it will light up the LED. So do you have any question or what, anything else, anything you didn't understand in this alarm circuit, or you didn't understand it all? Yulis, what do you think?
I think it's fine.
Okay. Joseph?
I think I have an idea. I'm kind of more like, let's see what happens kind of thing.
Okay. So I will explain a little bit more what it is, okay? So that will help you in the calculations. So what we are doing here is, so this is the op-amp configuration. Right now we are using this configuration, right? So in this configuration, what we are doing is we are putting, what you should say, one of the input, and we are saying, so G is V naught over V in, V naught over V in. So what we are saying, so this is inverting configuration, this is non-inverting configuration. So we are multiplying V in to get in V out, where our V in is whatever that is coming here. So if we see that here, what it is coming, V in, which is IL or M. So basically what we are trying to do is we are comparing our this current with the reference current, right? So to check, I will discuss that too. So what we are saying, IT should be defined as 110% of nominal IL. Why do you think we should define IT as this one? What we are doing, what do you think we are doing here? Herschel?
So we're taking a current and comparing it with other sources to see if it will produce red or green.
Yes. So what we are doing, we are comparing this current. So this is our source, right? Whatever coming in this current, we are comparing this current with this current, okay? We do not want this current to be greater than 55 milliamperes, which is more than 10% of 50 milliamperes, right? So that's why what we are saying is that 110% is 55 milliamperes. So what we are saying is that if we set it as a 55 milliampere, then when we compare it, whenever this gets bigger than 55 milliamperes, it will turn the red LED.
And
Does this make
also,
sense?
yeah, and also, what about if it's IL is equal to IT, like because it's shown whether it's greater than or less than? What about if it's equal?
So yeah, that's a good question. So what happens is that normally um, it doesn't, if that is equal, it takes it as less than until it gets greater than that. Okay,
Yeah.
and it happens very very in what you should say, rare scenario. Another thing I want to ask is, why do you think, so it should be 12 volt DC. Why do you think here we are mentioning this voltages, 12 or 15? What do you think? Anyone else want to comment? Benjamin, why do you think we should write this here as it is? Do you think that any op-amp is going into the saturation?
I'll be honest, I don't really know.
Okay. Ellie?
I'm also just a tad bit lost.
It's okay. That's what I
Sorry.
want. I know it's hard. I know it's hard little bit. So I want you to, you know, spend time on this thing so that we understand what's going on. So, okay, 1 minute. I will explain it. So what we are doing it here. Okay. So this is our open loop gain, right? So open loop gain means we do not have any feedback in the op amp, right? So what is happening in open loop circuits, that if you have op amp, you give it a negative input, and if your positive is grounded, what happens is it will have an open loop gain multiplied by input. And normally op amps have very, very large open loop gain. That's why what happens is, we know, I think from ENG2 and 4, whatever supply we will give here or here, this is the maximum thing. So if this V naught is getting greater than this supply, we will have a saturation condition. Do you remember this? Do we remember this?
I think so.
I honestly do not remember this.
Okay, okay. So we will go again with this, okay?
Professor.
Mm-hmm.
So what you're saying is the input voltage can never be higher than the source voltage. It just level out
Yes,
based on that.
yes. What I'm saying is that, let's say here, so with the op amp, you always have these supplies, right? Vs plus and Vs minus, where you all the time, except input voltages, you are actually providing them a supply voltages as well. Do you remember this? This form of op amp, do you remember? In ENG2 and 4?
Yeah, I remember it.
Anybody else?
I remember it too.
Okay. So you remember that whenever we exceed the voltage from this voltage, or decrease the voltage more than this voltage, what happens is it saturates. It does not give you voltage that is greater than this, right? So if our input voltage exceeds, then let's say if you are providing it as a 12 volts, what will happen? It will just produce 12 volts. If it is less than 12 volts, it will give you the logical result. Like if it is 4 volts and it is supposed to give you uh, like this output is 4 volts, it's fine. But as soon as it's becomes greater than VCC or minus VCC, it enters in the saturation state, okay? I think I should go through the last lab of Opamp that we have done.
I think a filter can reduce the saturation.
What?
I think like a filter, either high pass or low pass.
Yeah, but we want it to be in saturation right now. But okay, if you don't remember, it's okay. But right now, what I'm trying to say is when Opamp works in open loop condition, so there is AOL, which is the open loop gain. So open loop gain is very, very high for op-amps. Most of the op-amps have open loop gains in 80s and stuff like that. So it means that when the op-amp is in open loop configuration, it will go in the saturation, okay? So what happens is when you are using it as a comparator, like this one, so if your V1 is greater than V2, it will be in the saturation in this range. If V2 is greater than V1, it will be in this state. So it has always extreme cases for the open loop comparator, okay? Because its AOL is very, very large. Let me show you the data sheet of Opamp, okay? Okay, just a minute. Can you see this data sheet? Right?
I can see it.
Okay, let's go. So this is the normal op-amp, right? So these are the offsets. If you go down, we know that these are non-inverting. So do you remember this thing? We did op-amps, right? Okay, if you go down, so these are the limits of the supply voltages, right? So minimum you can give minus 15, maximum you can give 15. So I think we are recommending minus 12 and 12. So which means that its output cannot exceed or decrease more than its supply voltage. Other than that, if you see its open loop gain, let me check if there is. Hmm.
What you said earlier, you said that open loop op amps, they're always going to be saturated one way or the other.
Yes, that's what I'm trying to say. Yeah.
So the output is going to be binary, either plus VCC or minus VCC.
Yes, until they have a very, very large supply voltage. You know, what I'm saying is if their supply voltage is lesser than their open loop gain, then it will be always in saturation, you know. Let me check open loop. So normally open loop gains are very, very high. That's why we are saying that it operates in the saturation condition. So if you see here, what we are trying to see, can you see this slides? No. Can you see
We
them?
can't see it.
Okay, just a minute. Okay. So what we are trying to say is, let's see this thing, right? Here, so right now in your alarm circuit, you have two types of configuration. One is what you are saying is the non-inverting configuration, and the other is open loop gain. So in the non-inverting configuration, it's okay that you have what you should say, V out is equal to let me try to write another time. I don't know why it's not letting me write. Can you see my writing? No. Okay.
Yeah, I can't see your writing. I can only see a red box.
Yeah, just a minute. How can I write on this one? Let me do this. So what I'm trying to say is, in the non-inverting case, it is V naught by Vn is equal to 1 plus R2 by R1, right? That you can see, right?
Yeah.
So when this Vin will go here, it will become V naught is equal to 1 plus R2 by R1 multiplied by Vin, right?
Yeah.
Got it? So now your Vin is what here in this case? Your Vin is ILRM, right? Got it? Am I right here? If I make this font smaller. Are you getting this thing? Or not? So here, for the non-inverting case, it is this thing, right? Are we clear about this?
Yeah, we're clear.
Okay, so here it means that our V naught is fine and our gain is within certain parameters, right? So we are not getting, maybe we are not getting towards the saturation here. Here, saturation can also occur if your V naught is, or yes, if your V naught is greater than the supply voltage, okay? But here what we are saying is saturation will occur because there is an open loop gain involved. This is not closed loop. There is no feedback loop, right? So there is an open loop gain involved. That's why whenever one of them will be greater, you will either get plus 15 or minus 15. Does this make sense?
Yes.
Little bit clear?
Definitely.
Okay, so if we move further, so what we are saying, so this part is the third part, this one, right? And this part is the non-inverting part, this one, okay? Okay, so we are saying that that's why we are operating in the saturation region. So whenever one of them is getting bigger, our red light will turn on or green light will turn on, okay? So, okay. So right now what we have to do, we have to find out um, the values of the components, okay? We are designing an alarm. We know the input voltage. We know the currents that we have to deal with. So we will design the components, okay? Or we will design and like what is the value of RL, what is the value of R2, what is the value of R1? That's what we are trying to do. So here are the design values that we need to calculate. So calculate the nominal resistance, okay? Load resistance, that is RL. So nominal load resistance is RL here. And what we are trying to do is from the following nominal values, when your Vs is 12 volts and your IL is 50 milliampere, right? You are thinking that your RM is almost 0. So you will calculate your RL, okay? Then your RM will be 2% value of your RL. So it's very, very small, making sure that all of current is drawing towards the Opamp. So RM is very, very small. That's why we are trying to draw all of the current from here to the Opamp, okay? So what I will do here, I will, like I have pre-assigned breakout rooms according to your groups that you have sent me. So what I will do, I am going through all the calculations. I will give you 30 minutes of your time to do the calculations, okay, in the breakout rooms. So you will discuss with your partner, you will do the calculations, and then you will come back and show me your calculation, what you have done, okay? So we will compare whether your calculations are right or not. Sounds good? Is it fine?
Yeah, sounds good.
Those who have not told me their partners, I will randomly assign them today. And if they like, they can keep those partners or they can change them later, okay? Sounds good? Okay, so these are the calculations that are actually, I think that you have to do, okay? Are these a calculation in the document as well, or should I upload this slide? I will see that later. Okay, so these are.
Yeah, it's on the document. Sorry to cut you off.
It's not in the document.
It is. It's on.
Yes. Yeah. So because these are the old labs, and these are all the defined labs. Okay. So these are the calculations that you have to choose one of them, which you will do to calculate the power. So which one is available to you? Okay. So you have to decide which will describe the power rating. Okay. So now what is left to be calculated? Okay. So we know now IL, we know RM. So we can find out what is VM1, right? We know RM, which is 2% of RL. So we can find out what is the value of VM1. Now I want you to take VM2, that is the reference voltage as 6 volts, okay? And then put it VM1 from here up and try to calculate R2 and R1. That's the only thing that is left to be calculated. You need to calculate R2, R1, RL, RM, and all other things are set. Okay? Sounds good? Any questions?
So the calculations have to be done from slide 9, 10, and 11.
Yes. So you ready to go in the breakout room? Or do you have any questions?
Is this lab due next week?
No. This lab is not due next week. Today you will be doing calculations and the simulation. Next week we will be doing practical, and then this lab will be doing after the next week. Okay?
Okay.
So after we do calculations, we're coming back to the main room.
I will take you back. So you will be coming back, and then we will comparing the calculations.
All right.
Sounds good?
Yeah.
Ready to go? Okay, what is... Yes, Herschel, I will use next time. Okay.
Takes some time, but you'll get used to it.
Yeah. Okay, why it's 3? I made 5. I don't know. Okay. I don't know why there are 3 rooms. Okay, let me assign. So Sean, you told me Benjamin. Yes, you both are in one room.
I'm
Oh.
also in that room. Or
Michael
that should be.
Bond. Yes, okay. That's fine. And okay. Okay, and then Zane and Nicholas, you are in one room, right?
Yeah.
Okay. Okay, 1 minute. And assign Zen, Nicholas, you are in one room. Okay. And then, so the people we are left with, Ellie, Darian, Chris, Jack, and Joseph. So Chris, I can put you with Jack. That's fine.
Yeah, sure.
Okay.
I actually emailed you earlier that I was going to be partners with Jack.
Okay. Sounds good. So Jack, Chris, and
Darian.
Darian. Okay. Four, five, six. So last room it will be Ellie and Joseph. Okay. Okay.
Yep.
So we are good to go. 5, 6, 7. 7 rooms we have. Okay. And let me know if you can see the slides in the rooms too. Benjamin, you didn't join your room. I mean, all of you can use LT Spice, right? Right? So I will show you my output, and then, I mean, you can make your circuit on LT Spice, okay? Can you see the circuit?
Yes.
So it's just, I hope you will make it a little better, but it's just, I made it like that. Okay.
Which op amps do we use for these for this circuit?
So if you go in the component, I use universal op-amp. You do this. So you op-amp 07 is also fine, but I do this one on universal one, okay? If I do this, it will be the same as this one that I'm using, okay?
Yeah.
Okay. So what I have done, I actually created the same, what you should say, circuit as it is, using 240, 4.8 ohms, 12 volts. And instead of making mess here, like I just made the circuit like this. And at the open end, I wrote VCC by just label net, okay? And similarly here, I just write minus VCC and add them here, both sides. And similarly, I use the label net. So if you are using the same label net, it will take the voltage that it is creating here, okay? So it means that I am giving 12 volts and minus 12 volts at both ends, okay? Sounds good?
Yep. Sounds good.
Sounds good.
Okay, and this is non-inverting op-amp because I'm giving it in input here. And feedback resistance is 21.5, it could be 7. And then here I'm using 1 kilo ohms. This is my open loop op-amp. I'm giving it a 6 volt, 1 kilo ohms, and LEDs. So LEDs are actually opposite to each other. If you see that this wire is going to the negative and here it's going to the positive, right? So it's opposite to each other. Okay? Sounds good? So now the question is, how can we check that we are increasing the voltage, right? So what is happening? I am sweeping it from 6 to 18 volts, V1. Okay? So we designed it for 12 volts, right? Like we design our circuit for 12 volts, right? It means that once we are exceeding 12 volts, or once we are exceeding the current, it should change its voltage. Like we should see here something different, right? So that's what we are trying to see. Okay, so we understand the circuit. Should I run? Okay. Okay, let's see. So here I am changing it from 6 to 18 volts, right? Okay. And so the current is going from minus 75 to minus 25. Let me see that.
I think it's going down. I noticed the current falling as the voltage at node 2 is rising.
Yeah. Just a minute. should we see current here? Yeah, I think this is the current we should look for. So the current in R1, because that is going here, right? So the current in R1, if you see here, it is going from 6 volts. So it means it is going from somewhere less than 40 milliamps to the 80, 70 something milliamps, okay? So according to our design, around 55 milliamps, we should see the difference, right? Okay. So this is something we are seeing here, okay? But let me and okay, just a minute, let me run it again. One thing I want to show, they both are opposite to each other, right? The current through ID1 and ID2. So it means that for certain time, ID2 was on and the other time ID1 was on, right? Sounds good?
Sounds good.
Yep.
And if you see here, this point should be 55 milliamps, right?
Right.
Where is my cursor? Okay, let me move this one. Not this one. It's showing me, okay, this one. Somewhere here, right? Okay. So the changing condition is on 55 milliamps, right? This is my cursor here of IR1.
Approximately, yeah.
Yes, because I did 21.5, not 7. So maybe it's because of that. But that's what I wanted to show, that your final LEDs are opposite to each other. And at 55 milliamps, they are changing their condition, right? Are we good about this? Joseph?
Yes.
Do you have any question?
I have none. No.
Okay. Gianna, do you think we are good?
Yeah.
Okay. Chris, do you think we are good?
I think so.
Okay. So that's what you have to do for now. You just need to make the simulation, like the circuit on the LT Spice or P-Spice, whatever you are using, and try to see it's working or not, okay? Should I post this? I will not. I don't want to post this picture. I can actually.
You might forget though if it's not posted.
Forget what?
Simulate what it looks like here.
Yeah, I will post it. It's okay. I just don't. It's the same as the picture that you have on the slides, but I will do that, okay? But so you will make it in LT Spice or P Spice and try to see your simulations, that whether they are working or not. And next time we will be doing the practical on the kit. Make sure that you get your kit before that, okay? Sounds good?
Sounds good.
Any questions? Okay.
This
Yeah,
lab is
go.
due in 2 weeks. The lab is due in 2 weeks.
Yeah, Yeah,
When's
yeah.
the due date?
So I will upload the due date, but it will be 1 week after we will complete the lab.
Okay.
Okay. So if we complete the lab by next week, which I'm thinking we are completing it, then it will be due after that. Okay.
Okay.
And on the document, lab document, it's mentioned. So I will come to the lab document, but do you have any question regarding sweep? Do you have any question regarding anything else? So this is good. I can stop share.
So the sweep is from 6 to 18 volts at 0.1.
Yes, 0.01 increment. And which I have done from here. If you go transient, you can do transient, but here I'm using DC sweep. Okay. So I will stop share and let me talk a little bit about the document. I don't know whether I have this here. No. So just let me have this one. So in the document, it's very, very clear what you have to do in the lab document. And so just follow the instructions. And as it is a, the group document, so it should not be, I think, difficult to complete, and I hope it will not be tedious. So if you open the document, it actually outlines that what you need. So calculations we have done, LT spice circuit you will do, and the measurement part we will do later, and then we can fill out the tables. Okay. So I think it's similar to the lab reports that you have done before, but so there is little bit of hypothesis and background and research. So put them, what do you think is appropriate? Like background, and in background and research, you can put like, what is comparator, what equations, what do you think comparators can do? And in a hypothesis, you can present your hypothesis, right? So it's, I can understand that each group will be doing different, but I expect a similar template. Okay. Sounds good.
So the hypothesis goes in the introduction.
One, I just see that. So it not necessarily be an introduction. It's just you follow the same what you should say headings, like background and research, hypothesis, and procedure. That's it. It actually both of them should be an introduction, right? Yeah.
Okay, thank you.
Okay, then we are good to go for today. And I actually uploaded the minute paper on the Canvas. Please fill that out and give me feedback so that we can see what we can do in the next lab better. Okay? Sounds good?
Yeah.
Okay, then thank you for today and see you next lab.
Thank you.
Thank you.
Thank you.
Thank you.
Bye.
Bye. Have a nice day.
Too.